So it's now my great pleasure to introduce Kieran Cox, who comes all the way across town to visit us from our sister campus at SFU, where he's a postdoc in Isabelle Cote's lab, a name that's familiar to many people in this seminar. He is at Liber Aero, is that how you pronounce it?
Liber Aero.
Liber Aero and NSERC postdoc fellow. And he's also, I did a bit of digging. He holds a Sailor Sea Fellow at Western Washington University.
Just got that too.
Oh, congratulations. He did his PhD at UVic, and he works at the interchange of sort of fish ecology and climate change. And a lot of his work, as he'll tell us about, involves sound in the marine environment. He has also co-founded fishsounds.net, which combines expertise in ecology, bioacoustics, and data management to consolidate fish acoustic research into a publicly available web portal, which is a resource I was playing around with a bit last night. It looks really fantastic. So Kieran's going to tell us about his most current research.
Yep.
And let's give him a big IOF welcome.
Thank you. I feel like you should just be giving the talk. That was better than I'm going to do. Okay, so for the folks at home, I'll likely stray a little bit from the mic, so feel free to let me know if that becomes too far away. So yeah, thanks for the invitation to speak with you today. I'm going to be talking about our ongoing work into underwater soundscapes. And so I live and work across the Huu-ay-aht, Snuneymuxw, Musqueam, Squamish, Tsleil-Waututh, and Coquitlam nations territories. And I'm very grateful to these nations for their stewardship. I'd also like to acknowledge and thank the many folks that make this work possible and the funding agencies that support us. So how do species navigate this kelp forest? How do they communicate with conspecifics, avoid predators, and find their prey? Right? These are broad and long-standing questions in ecology. Do species navigate this coral reef 1,200 kilometers away using similar mechanisms? Well, if we consider a representative individual, say this copper rockfish, we might assume the species navigates its environment using visual cues, much like you're seeing these photos. But for the taxa living in these systems, light and as a consequence, color declines actually quite rapidly with depth. And so we can say that visual cues have a pretty limited range. So what about chemical cues, right? Taking advantage of olfactory systems. Well, if you spent any time in these environments, you know they're not static, right? And chemical cues can move with the current away from the intended receiver, and at bare minimum, they're fairly unpredictable at times. So what about sound? Well, sound is 800 times denser than water. This means that it travels, water is 800 times denser than air, and this means that sound travels at about 5 times the speed. So the information embedded in sound is moving at 1,500 meters a second compared to 350 in air. It's radiating in all directions, so it can get places quickly. And what this means is that species can pass this information over vast distances, perceive their environment quite accurately if they're able to detect it. So these three kind of visualizations illustrate a species listening, olfactory, and visual spaces. Now, the distance of them is going to vary a lot by taxa and ecosystem, but their order may be relatively conserved across species. And we know that fish are able to detect the information that's embedded in sound using a series of mechanisms, one of which is the otolith, which in many ways is really analogous to the human ear. And there's always someone thinking it, and they're afraid to ask. Fish do not have external ears because of the relative consistency between tissue and water, right? And this allows sound to travel to the inner ear without the aid of an external structure. Many fish also possess secondary hearing mechanisms, such as the Weberian apparatus. And in this case, it's a pair of 4 bones that connect the swim bladder to the inner ear, increasing hearing sensitivity. Basically, it's acting as a particle motion or a pressure to particle motion transducer. Fish also possess one or several lateral lines. And structurally, these are actually quite similar to the cells in the inner ear, and they're really good at detecting particle motion in the near field. And fish use this hearing ability to detect a wide range of ocean sounds, which we can term the soundscape. But they also contribute to the soundscape, and they do so using a series of mechanisms. They can track their swim bladder with sonic muscles, beating it much like a drum. They can strangulate bones by grinding them together, or they can release gas through their mouth or anal cavity. And this is kind of the classic example, which is that herring release a fast repetitive tick, otherwise termed a fart. And so when we look at why fish are making these sounds, we see that, yes, certainly under captive conditions, the vast majority is associated with distress, which, right, that makes sense. If you're being caught or handled or hurt, you're going to make sound, and fish are very much doing the same thing. But when we look under natural conditions, we actually see that the most of the time it's associated with reproduction. And this is to coordinate spawning events and find mates. So how many fish are making sound? Right, this is really a fundamental question in the field as far as we see it, right? It's the base of so much of the work that we want to do, and it had been unanswered for quite some time. So to consider this, we first define two types of sound, active and passive. Active being sounds that are made intentionally by an individual. We'd call that individual soniferous. Passive being the byproduct of an activity. And so to answer this question, we extracted literature or data from 900 sources of literature. And when we look across fish phylogeny, shown here with a black line indicating every time a species is soniferous, we see that it's taxonomically widespread. Specifically, it occurs in 133 families and over 900 species. And these species are globally distributed. They occupy every body of water classification that Fish Base, I don't need to tell any of you, the leading authority on the distribution of fishes, designates. And when we look at where they're concentrated, certainly the highest levels of soniferous diversity are in the tropics. But when we consider the rates of soniferous diversity relative to the species in the area, we see the reverse. And your relative sonifery, if you will, is elevated in temperate regions. And we can assume this isn't a data bias because far more work occurs in the tropics. And so what we think this is likely that in areas where the water is more likely dark or murky and sound becomes more advantageous, you're going to see elevated rates of sonifery occurring. So these estimates are all living numbers, right? They're constantly being updated. The reality is we've examined less than 4% of fishes to find out if they're soniferous. And so with this in mind, we didn't really want to just publish a paper every couple of years with an updated number in it. We launched the Fish Sounds Project. And this allowed us to consolidate all of the data from our original review, but also easily conduct additional rounds of data collection. So we've been able to bring the number of soniferous species documented to 1,048. We've also been able to archive over 1,200 recordings of these sounds. So this is now the largest global repository of sound production in fishes. It allows people to search by taxa, region, download all of our data, and use it freely. Really, it's just a way to showcase the work that's been done. And we've been pretty impressed with the global interest in this topic, shown here as daily use in April 2023. And so since we launched in 2021, we've had over 300,000 page views, and we see about 20,000 annual users, and this goes up every year. So go check out fishsounds.net. Your favorite fish is probably on there, play some sounds. But really, this data has allowed us to ask questions that are important to the work that we do locally. So combining the fish sounds data with fish-based data allows us to determine that there's 74 species of soniferous fish, like right out our door when we're doing our surveys. Now, predominantly, these are rockfish. They make quite a bit of noise. They'll commonly talk to each other and run away. These kind of things are easy to see. But it also includes sculpins, herring, and salmon. And greenlings, it's quite a diversity. And the sounds they're producing really range. So this includes like the hum of the midshipman, which hopefully some folks are aware of. This can go on for hours as males try to attract mates. Salmon make quite complex sounds. This actually hasn't been named yet. It's an issue in the soundscape world. People can't agree on names. And herring with their fast, repetitive tick. Now, the cacophony of biological sounds that we've put forward through fish sounds doesn't exist in isolation. Species are contending with ever increasing amounts of anthropogenic noise. And when we examine what the impacts of this may be on fish, we can use a meta-analysis to consider a range of species and experimental conditions. When doing so, we plot response category and magnitude of the response, allowing us to see if data falls above and below the line. If it's above the line, it means there's an increase in that category. Below the line, a decrease. On the line, no change. And so we see that fish, when exposed to noise pollution, they're going to forage less often. They're going to move more frequently, especially engaging in startle responses, and they have an elevated cost of reproduction. Now, any parent in the room knows this is the most costly thing you can do biologically, and so that's not ideal. They also have a hearing threshold shift, which indicates they become temporarily deaf to certain decibels or frequencies. And these stressors register in their blood cortisol, their primary stress hormone. Now, fish are far from the only taxa that rely on soundscapes. We really think that including invertebrates in this dialogue is essential, as we know that they're living in an increasingly noisy world as well. Again, using a meta-analysis, which was led by Haley Davies at the University of Victoria, actually just published 3 days ago, we can see that synthetic sounds, so those made by computers, are going to negatively influence invertebrate behavior and physiology. Natural sounds, including those made by fish, and oddly enough, music, as this is a topic in aquaculture, increase or have positive influences on their behavior and physiology. But the anthropogenic data is really the interesting part here, I think. We see that, yes, there's an impact to both. It's more pronounced within physiological responses. And perhaps this is because we would assume that physiological responses will precede behavioral ones, or maybe their magnitude will be more severe. But when we look into this in more detail, what we actually see is that anthropogenic noise increases the recruitment of invertebrates. And it does this because many invertebrates use sound to hone in on their ecosystem and decide where they're going to settle. This happens despite the fact that when they land in that system, they're then going to be less able to defend against predators. They're going to suffer a cost to their movement, and there's going to be a suite of physiological impacts, including their genetics, biochemistry, and morphology. And this is really, I think, what makes sound very complicated for many of the kind of management discussions we would have. It is both a signal by which species navigate their environment and also a pollutant. This would be like if climate change species were using temperature to communicate and then also getting impacts from temperature. But how pervasive are these impacts, right? We're seeing this across these species, and really that question is a function of how much noise pollution exists in marine areas. And there are unfortunately not great estimates on this. It's a tricky thing to figure out. But after 2 years of noise modeling, we've been able to develop a pretty comprehensive picture of what the coast sounds like and how it may have changed since the Industrial Revolution when we started putting combustion engines on the water. Specifically, we've modeled minimum, average, and maximum noise levels along the coast, considering 14 vessel categories, wind and wave sounds, so ambient conditions, at 3 depths and 6 frequency bands. And the aim here is to put out a picture that's really relevant to anyone interested in this conversation, and certainly all the taxa in the ocean. Now, we've done this for British Columbia's entire exclusive economic zone at a 3 by 3 kilometer resolution, but then we've also done it in 8 regions at a 200 by 200 meter resolution. And the mismatch here is just really a computation issue. These entire process took about 2 years of pretty high, high capacity modeling. And when we look at what the coast would have sounded like, potentially before the Industrial Revolution, but certainly just the contribution of wind and wave sounds, we see that 70, 80 decibels is quite common throughout the entire coast. This is broadband noise at 10 meters depth for the acoustics folks in the room. But again, we have 6 frequencies and 3 depths. When we consider the average sound levels that you see on the coast today across all the vessel categories, you see that reaching 120 decibels is quite common, and in some places we're exceeding 150. When you look at maximum noise levels, so this is the loudest that any given map cell gets, 150 to 170 decibels becomes very common. The difference across the entire coast between maximum and minimum is over 50 decibels. Now, obviously, many regions are well above this, but that's a coast-wide average. Now, just to put that in context, 50 decibels is the difference between a typewriter and a rock concert. So we're now using this data to try to gain some insight into how species may be influenced by this. If we take an example like the Pacific herring, we know that it has a dose response rate of about 123 decibels is going to cause an adverse behavioral response 50% of the time. And we can use this to set a threshold and say, okay, where is that exceeded? Well, under ambient conditions, we see that it doesn't occur on the coast. Under average conditions, we see that it's primarily shipping lanes that would cause this response to occur. And under maximum conditions, it's actually, kind of unfortunately quite common. Now, this is a very preliminary analysis as we just received funding, as mentioned, from the Salicy Institute and the CDOC Society to look into this in more detail. And my next postdoc will be conducting this analysis for herring, killer whales, and salmon to try to build kind of an ecosystem picture on this topic. And I really think this is an important way to manage soundscapes on the coast, but fundamentally I'm a community ecologist, and you kind of always need to consider what's going on in the ecosystem. And so a few years ago, I was diving on a kelp forest with Tom Reimken, and I became aware of a stillness in the soundscape that most people associate with terrestrial forests, right? And in many regards, I think this is why people go to these ecosystems. They say, it helps me clear my head, I can think, I feel peaceful. I spend basically no time in forest, by the way. This is mostly kelp forest observation. And it's a great reason why you want Tom Reimken as a buddy, because he gets very, very into these ideas with you unless you sit and bubble underwater and think them through. But what I kind of determined, or at least think I determined, was that this service, the conservation of the soundscape, if you will, is a function of the composition of the kelp or the tree forest. So composition, density, area are all going to influence this service. And what that means is that as these habitats decline, the service would as well. The process looks something like this, where in a healthy kelp forest, your noise pollution is blocked, and this conserves the listening and communication spaces of your species, shown by this circle. But as your kelp forest degrades, as your kelp forest degrades, more noise pollution enters the system, and your communication and listening spaces decline. Do you want me to?
It's still online.
All right. Joke's on you for coming to a talk for once. I always, whenever I give these talks, I want to be like, brought to you by sound. There's like a kind of a funny element to it.
It's still on. The projector.
Chris, I remember when I was on Calvert and I saw your talk go down, and then you did like kind of an interpretation of C-star Wasting's disease and the data. It was, as an early grad student, it was like exactly what I needed to see, where you're like, okay, so this guy's gonna, he's like, okay, your arm's over here, and and then the data looks like this. And so I'll finish this talk that way, I think. Do you want me to unplug this and plug back in, just in case?
No,
Nope.
not that. If anything, it's this, because the audio is still working. Oh. That's good. Wait.
I think you're gonna need me to do.
Oh, there it is.
There it is.
Yeah.
Are we on one? Okay. Sorry about that.
Everybody good online? Cool. Okay, sweet. I really think that like Talks in the Modern World can't be a talk if there's not some tech issue. We worry like crazy about it, and it's just such a common thing. Okay, so yeah, so the point is this, that as the ecosystem degrades, you get more noise pollution entering the system, and this is going to cause a decline in listening space. Theoretical relationship is going to look something like this, where habitat degradation allows noise propagation to increase. Now, the slope of this line will be really influenced by the specifics of the habitat. So how dense is it? How much can it block noise? Basically, for every unit lost, how much can it maintain that service? So in a kelp forest, where they have air that actually blocks sound quite well, you can have many different structures. We might assume that the slope is going to decrease, where a less dense and less absorbent seagrass meadow nearby is going to increase the slope. If this is true, then what it means is there's a mirrored inverse relationship between habitat degradation and listening space. So as this increases, listening space declines. And degradation in this case can really be driven by many factors, right? This can be noise pollution causing the decline in the habitat. But the real elephant in the room here is changing climatic conditions broadly simplify habitats. And once you have habitat degradation, you then have noise pollution levels increase, which sets in motion a suite of mechanisms related to that, and ultimately influences the biological community, reducing its stability. And this would start a feedback loop that would continually degrade the system. Now, if this is the case, then it means that ecosystems and really the soundscapes surrounding them could exhibit stable acoustic states, as we're calling it. And then they would go through some sort of tipping point and decline, right? And so these would be distinguishable based on their soundscape. Now, this is just a theory, right? We call it habitat-mediated soundscape conservation. The paper actually comes out next week, but it's important to test this, right? So I spent 6 months living in Bamfield over the last 2 years, conducting this work in kelp forests. But as I also think that it's a cross-ecosystem phenomenon, we spent a month in Belize at the Smithsonian's Marine Station, testing it in coral reefs and seagrasses. In all cases, we're working in at least 20 sites, thus hundreds and hundreds of dies. But really, there's a shout out needed here for the two folks in particular that made the Belize work possible. There's Audrey Luby, who was a PhD student at the time at the University of Florida, who's leading the seagrass and the coral work under my supervision. And Audrey's now come to UVic to start her postdoc, which is fantastic. And M. Lim, SFU PhD student and UBC alum, joined us in Belize. And these are really like the two ideal people to spend a month on a very small island with doing this work. And so in all cases, the surveys are relatively consistent, but we'll take a kelp forest as an example. Divers are heading in. We're doing a reef life survey to quantify the biological community. We're surveying the kelp height, area, biomass, composition. Deploy a set of hydrophones 5 meters apart. Put out a set of cameras to observe species responses. And then we introduce noise pollution. And this is by a boat and a speaker. And the speaker allows us to introduce specific frequencies. And then we're replicating this across a range of habitat conditions, effectively with the aim of quantifying this relationship. Now, the analysis of this work is still ongoing, but I can share some early results from the seagrass work. Specifically, that multiple habitat metrics, in this case, seagrass density, are correlating with attenuation. Specifically, we're seeing about a 4 decibel change in sound pressure levels as seagrass density increases. Now, kind of the ecological implications of this become, well, what does 4 decibels mean for species living in seagrass? And we're still processing our data on this, as we have behavioral response data and ecological community data. So in the interim, we've got to rely a little bit on the literature. So if we take an example from the Gulf toadfish, which occupies seagrass systems, we see that a 7 decibel increase in noise results in a 4 to 5 decibel, or sorry, 4 to 5 fold increase in cortisol levels. And so we do think that what this means is seagrasses are having a meaningful influence on the amount of acoustic refugia these species receive. And for those of you that think a lot about coral reefs or kelp forests, yes, our early data on this topic suggests that they're blocking noise more as a function of their structural complexity. So we know that noise pollution is pervasive. It's likely having its impacts exacerbated by changing climate conditions. But what can we do about it? Well, Canada is developing an ocean noise strategy, and I'm not going to go into my policy work on this topic because honestly, that's an entire other seminar. But what I will say is this document is unlikely to move the needle on conserving soundscapes, so to speak, for at least the next decade. And so in the interim of that, what we're really focusing on is raising awareness around this topic because it's going to be public pressure that moves things forwards. And we're doing this through our Fish Sounds Educate program. And we think this can promote ocean literacy as a whole and also act as a model for how scientists can increase the likelihood that the work that they're doing enters the public space. Fisheries and Oceans Canada funded this project as it aligns with their conservation targets, and it's allowed us to hold or participate in events for school-aged children, lifelong learners, many communities. And yes, that is a game called Fish or Fart, which we thought would only do well with children, but actually it spans all ages. And it's kind of funny, but it's also really neat in that it's a way to use kind of humor and the exciting aspects of biology to then talk to people about ocean conservation, noise pollution in a way that's a little bit less formal, but you know, every person in this program is just a top-rate scientist, and that's been really neat to see them kind of work across those boundaries. The uptake's been pretty incredible. We've been able to work with many great organizations, and we just sent the final version of our coloring book to the printers. If anyone wants one, you can send me a message. So far, we've held, in the last 2 years, we've held 71, or held or participated in 71 outreach events, and we've reached about 3,000 participants. And as a young scientist, this was really neat to me because this is a DFO-funded project where basically we said, we want the metric to be that we will influence people's awareness of ocean conservation. And DFO said, yeah, we'll fund that. So that's really exciting. We're also hoping that we can kind of use this to change the way we do science a little bit. We've kind of been taught this method in grade school. And one of the problems with it is it can kind of exist in a vacuum, right? And so we're saying that we can open it up and we can just add one simple step where the onus is on us to inform society of the work that we're doing. And then we gain insight from society on how we should proceed. In this case, ocean soundscapes, but this is really starting to affect a lot of the work that we do. Okay, so we covered a lot. I talk really quickly when I get excited. So let's take home some points. At least 1,000 species of fish produce sound. And again, this is just an underestimate. We've examined 4%. 74 of which occur locally, and you can check out who this is and the sounds they're making on fishsounds.net. Coastal noise levels have increased by over 50 decibels. Anthropogenic noise is influencing species' ability to navigate their environments, and this is likely being exacerbated by climate change and habitat loss. And really, I think that the route forwards here is going to be a combination of education, habitat protection, and regulations. So again, I'm just to reiterate how grateful I am to all the folks that support the work we do, especially those who spent 215 days at remote research stations with me over the last 2 years, those who fund our work, those who steward the lands that I live and work. I'll take any questions.
Yeah, thanks very much, Kieran.
No problem.
Hobble up here. So if you have questions online, please either raise your hand and you can read them out or you can type them into the chat. Nope, that's good.
It'll come through.
And what I'm going to get you to do from questions from the room is just summarize them for the people online. So I guess we'll start with questions or comments from the room.
Hey, Alex.
Yeah, so I'm curious about what benefits you think marine protected areas could have, in terms of like maybe being a quieter zone for fish species and anything that's kind of utilizing that habitat.
Yep, absolutely. So a lot of the sections that I talked on today. Oh, sorry. The question was from Alex, who's a great grad student at UBC, and he wants to know what the benefits of marine protected areas could be for essentially creating some sort of acoustic refugia, which is a great question. So, yeah, a lot of the topics I touched on are quite large in the scope, and I only get a little bit of time per section. The noise analysis that we're doing on the coast right now includes looking at protected areas. So basically what we did is we took surround, and this is all done with Stephen Brownlee at SFU, who's just been fantastic. We took all of the protected areas on the coast, and I think it's about 80 of the rockfish conservation areas. We doubled them so they're the same size and characteristics and moved them into control areas, and we're looking at noise pollution in them. The kind of early take home is that it's not likely that they're causing any sort of acoustic refugia. This in some regards is kind of okay. It's not part of their planning to date, right? They've never said they were going to do that. It's not an aim. I think the big push is that if it is, then because noise is the byproduct of so many activities, we'll actually get a lot of things out of protected areas, right? So that's another analysis we're going to complement that, basically saying, if you were to clean up noise pollution in these protected areas, in some regards, we can skip the individual conversation about every stressor, make them acoustic refugia, and then you will, as a result, clean them up as a whole. Yeah.
Thank you so much. I just wanted, and maybe I was talking about how many sites you end up surveying, and how you actually chose those sites, and why they use.
Yeah, great. So the question was about the field work we've been doing, how many sites we surveyed, how we chose them, and why did we head to Belize. So the number of sites is 20 or more-ish in each system. That was kind of an aim. We wanted to do this as a parallel kind of coordinated global experiment concept. And so it's 20 in each system, and they occupy a very defined gradient of complexity, so very healthy. So in Banfield, the classic example is that you kind of have kelp forests that look a little bit what like they maybe used to look like, and then you have kelp forests that look like what they might look like in 100 years. And so we're working kind of across that gradient. Site selection is kind of a combination of who's doing other work there, and we can tie into larger biodiversity surveys, who else would benefit from these surveys. We're a big fan of trying to move data into many spaces when we collect it. We went to Belize, honestly, because I did a Smithsonian fellowship in my PhD, which for the grad students in the room, I'd recommend you look into. And I spent 4 months jumping between Belize and Florida. I was able to work there, and it was a really great system. And so, you know, I was talking to Audrey, we were talking about kind of the exciting things we could do. And I said, like, you know, let's go to Belize and do this. And yeah, it's a system we knew well, and, you know, we knew we could work in. So that's where we went, and the Smithsonian funded it.
And it was in Belize, so.
Yeah.
Andrew.
Yeah. Yeah, so you mean biological sounds, not anthropogenic? Okay. Yeah, absolutely. Okay, so the question is, what is the seasonal trend in the soundscape along the coast? And so certainly there's that, like the analysis we're doing of the coastal soundscape allows us to consider more or less every vessel class you would think about. And so we're seeing certain vessel classes have really binary contributions to the soundscape. So ferries don't run as often, several ferries shut down, cruise ships are absent, certain areas become less easy to navigate, vessels change their route. And so in that regard, I think kind of summer is kind of when we get a lot of peak movement on the water. You also get small vessels, tourists operating, anything associated with that. So I'd say summer is probably when you see a lot of peak noise. It's when the ambient noise conditions will be the lowest because you're not getting a lot of wind and wave noise. And that can be quite a bit of noise in certain places. In terms of fish, largely reproduction. So a lot of fish are communicating when they're trying to reproduce. The classic example, midshipmen come and they use those guys fight for territory, build a nest, and then they hum for about 9 o'clock at night to 6 in the morning every night. A lot of our hydrophones in Banfield just have these bands of males singing all night. They look like a generator running. So yeah, I'd say the soundscape is more active kind of in both fronts in the summer, and for fish, dawn and dusk will be kind of areas. The same is true. We have a snapping individual. It's not a snapping shrimp, but it's a snapping invertebrate on the coast, and it seems to activate around dawn and dusk as well.
Question in the middle there. Yep.
Hey, nice talk.
Hi.
I'm wondering about like thinking about the urban environment and like shoreline armoring, you know, all of these things that are getting poured in.
Mhm.
Especially with like that also.
Yeah, so the paper that's coming out in Trends in Ecology and Environment this week or next week looks at that topic exactly, right? So I'm saying that as your habitats are declining, so is this service. Well, it's kind of important to point to the fact that we are building habitats up kind of on mass and marine environments. I don't think they're providing that exact service because so many of those are generating noise pollution at kind of a micro habitat level. So you build a dock, yes, it's going to block certain noise, but you're also going to put off a lot of noise. There is a caveat there for like, well, they kind of could. And so as we think more about living shorelines, designing things in specific ways, certain kinds of structures, I think they can provide some element of that service to species. And we certainly see that. It's also a great argument for things like kelp restoration and coral restoration as far as a really high benchmark of recovery. These systems generally are scrambling to figure out what recovery means, and you know, a little bit of kelp or a little bit of coral doesn't seem to cut it. So, well, if you're restoring the soundscape of that system, like you've done quite a good job. It means you have species that are returned, they're making sound, they're recruiting other individuals, and so yeah, I think that's certainly going on. Your point's a great one. Sorry, I missed it for the folks at home. I've answered the question, so cart before the horse. But the question was about shoreline development and its implications for soundscape conservation.
JJ, do you have a question?
I mean, it'll certainly be a very noisy. Oh, sorry. Yes. The question is, with changing climatic conditions, what will the soundscape of the future look like? Will it be noisy? Will it be quiet? So certainly, you know, as a whole, it'll be much louder, right? We're moving huge amounts of goods all over the coast. The soundscape has increased. So even in areas where we've lost a lot of habitat, the entire noise, the amount of noise in that area has gone up generally. There's going to be a lot of changes, right? It's kind of in some regards, it's going to be simplified. We're going to have a lot of noise pollution. We're going to have far less noise or sound from cracking sea ice in the Arctic, which is a huge amount of sound in that soundscape. We're going to have less fish making sounds. We're going to have less coral reefs that make a lot of sound. So we're going to lose a lot of our kind of variance and our biological contributions and some of our abiotic contributions, and it's going to become noise pollution. And noise pollution in itself will have some range to it, and I think that's going to change a lot as well. You know, a really good example, there's now this algae anti-fouling mechanism that shoots out a very high frequency sound to essentially explode algae. That's about to be introduced on our coast. It's in a few cases already, but that's a whole new type of sound. From a killer whale perspective, it drops hearing down immediately. If they're close to it when it goes on, who knows? And so we're seeing this kind of, yeah, this sound revolution in some regards. So, yeah.
Did you have a question?
Yeah, I'm very interested in, great talk, by the habitat degradation implications, and you were considering sort of the noise overwhelming signal and that, you know, becoming unfavorable as you lose kelp. But habitat patches are also sending signal out as, you know, an attractant for recruits. Have you looked at it from that sort of reverse angle to see if degradation impacts sound transmission out to larvae or other things?
Yeah, so the question is about the degradation of a habitat. Instead of thinking about how more noise pollution may be blocked, instead thinking about how sound from that system is going to travel out further. basically thinking about the changing physical properties and how that's going to influence sound generated from within it. So yeah, you're spot on. There's been some work by Steve Simpson and his group that kind of show they're looking more about how degradation changes the soundscape. But it's not a very far jump from that to, okay, but that soundscape that you do see, how far are you detecting it out? It's one of the arguments we make in the paper for what's called acoustic enrichment. If you want to try to draw species into a system, one of the things you can do is introduce a sound and species will be drawn to it. You want to be very careful doing this because you could be kind of drawing them to their death, so to speak. But the argument there is that when you first start that, it's going to travel very far. The same is true with an ecosystem in general. And so I think that will be helpful. The one thing that I didn't show because I didn't want to get into it, obviously with the stable acoustic states, if we called it, there's a conversation there about hysteresis. So if your sound producing mechanisms are breaking down as your ecosystems degrade, your soniferous taxa are leaving the system, which is something that I'm checking in the data that we're doing, then you can assume the route to recovery is going to be much more challenging. So that's kind of my ongoing thinking about that.
I'm going to interject with a question. So you were showing us some graphs about the noise pollution on the Pacific Northwest, and you mentioned that you did it different spectrums. Do you see any trends and overlap between sound production in different groups of fish or types of sound that's being used and the frequencies that specific sources are giving off? Like, boy, a lot of noise is coming from this, and it seems to interfere with this type of species with this type of, activity.
Yeah. So folks at home might have heard that, but just in case, the question is about the match between hearing sensitivity effectively of a fish and the kind of noise pollution that's introduced. And so certainly you do. So hearing sensitivity is, people well know, is different across species. And so part of the herring graph is salmon. It's the other color that I didn't add a nice picture for. Salmon are deaf compared to herring, right? So from perceiving your environment, being influenced by noise pollution, and that registers in the slope of their dose response curve. It takes more noise at a certain frequency to cause salmon to respond. There's going to be entire frequencies that these species don't hear. So the reason we work in the 6 frequencies, I'm personally not a marine mammal person, but it's an important part of the conversation on the coast. 2 of those frequencies are just related to marine mammal communication and marine mammal echolocation. And so specific noise pollution sources are going to be right in that frequency. The algae anti-fouling mechanism that I mentioned, that's extremely high frequency, which is why it's going to be, if it comes on the coast in a big way, it's going to be really impactful for killer whales because it's right in that where if I'm underwater, I might not even hear it. Fish certainly might not hear it. Invertebrates, maybe not. So yeah, there's a real matchup there of who's getting hit by what. I think it's what I find really exciting about this pollutant. It's kind of, Chelsea Rockman wrote a great paper about plastic years ago called, it's like a plastic isn't a plastic isn't a plastic. I think there's one there about noise, right?
Sorry, there's one online. Okay, we'll do that first and we'll come back to you. Do you want to read it out, Natasha?
Asking, has there been any work looking at the impact of soundscapes on different life stages within species? For example, eggs, juveniles, spawning adults, different sensitivity to noise pollution?
Yeah. So there has, it's all kind of, the question online, which some of you can probably see in the chat, is about the impacts of noise to different stages of a species' life history. So as it moves through its development, is kind of all noise pollution equal? And the answer is certainly not. So when species are developing, they're going to be much more susceptible to noise pollution, and any of that pollution is going to have kind of lasting consequences. No, this isn't just a broad brush answer, I would say. It's going to change a little bit. The impacts are going to be different, but the concern kind of from the early life stages would obviously be that if you influence rates of development, survival, and then kind of more morphology, that's going to persist through time. So, it's no shocker that I think larger, older individuals can probably weather things a little bit better because they can respond behaviorally. And obviously, like in the case of invertebrates, if it hits them in their settlement stage, they might go to a kind of less than ideal habitat.
In one of your plots, there was a protective effect in terms of like the production pressure. with increased sound, I was wondering if there's any, I guess, like different, like speak more on that, if there's any other like. That actually.
Oh, so do you mean with fish or with invertebrates?
The invertebrate.
Yeah. Yeah, so it's actually not protective. Unfortunately, it's their ability to respond to predators. Yeah, and so and actually, this is a paper that I owe Chris with some work we've been doing with a student who's now at SFU. Sorry, for the folks at home, it was about kind of the interaction between perceiving a predator and noise pollution in invertebrates. And yeah, so unfortunately, if you're perceiving your environment with sound, and in the case of invertebrates, there's this kind of relationship. I mean, this is the case in everything, but there's a relationship between particle motion and sound. Sound is vibrational energy. There's two components to it, the sound wave and then the vibration, and invertebrates really hear the vibration. So if there's a lot of noise pollution in an area, and here I mean sense, quote marks for the folks at home, if you're kind of overloaded by that, you're unable to perceive a predator. And so you're not going to engage in the predatory response you need to do. You're more likely to get eaten, unfortunately, which like is true, right? If you're hanging out in an environment that's loaded with noise pollution, you're not going to hear anything coming.